breath.
All right, 7 o'clock, let's get started. All right, today it's review lecture 7. Actually, this is review number 6, but on lecture 7 on data abstraction. We have done the functional abstraction or function abstraction on taking out the purpose of a function and make it into a routine. And data is the same thing. There's this thing called abstract data type. We can use the data without knowing how things are actually implemented within the data. This is like you are going to see this thing more in lecture 8 also. You use tuple with the, for example, the count method or the index method without knowing how this is actually implemented. And you're going to use list with all these different methods without having to know how they are actually implemented. But if you want to know the time complexity of what these guys are, then you would have to go to the website that I gave you in the Python complexity. I think that it's a Python complexity page that I listed out in the forum. Okay. All right. So these are the kind of thing that we deal with in list and then also in dictionary and in sets. So for this should be the end of the midterm material. All right, the midterm material will be from until here, but inclusive of recitation number 1 to number 5, plus tutorial 1 to tutorial 5. Okay, so those will be the material that we will see in the midterm coming up in end of March. Okay, for today, what I'm going to show you are actually things that how you should learn. In some way, I think this is the way that we should be learning things. The learning is that is the statement I wanted to say. All right, you have to find the similarity and the differences and to know the various possibilities. Okay, what do I mean by that? You can see that tuple and list, tuple is very much like a string, the way that you can see, the way that you can take things out in as in string. List is also a collection of things, just like tuple. But list it's different from tuple in that list it's mutable, whereas tuple is immutable. All right. So you have to know the similarity between the two, and you also should know the differences. And doing that, it will make difference in when you're working with it. It will be different when you're working with it with them directly in one way, or you're working with them in functions, or you're working with them in recursion. So all these are the things. These are the 3 points that I wanted to cover for today, and hopefully this is your way of learning about them. All right, so we're going to see the differences. Mainly it's the mainly the differences mainly on one is mutable, the other is immutable, and the similarity in the sense that they are collections of items with order. Okay, and you're going to see this thing more explicitly as in lecture 8. There are this sequence and the differences in the sequence. One is called sequence, the other one is called collections. All right. Sequence are tuple, list, and string. Collection include tuple, list, and not the string, but the dictionary and set. Okay, so these are their differences and their similarity you should know. And about their various possibility, meaning that the way that you can use them to achieve whatever you wanted, it's going to be different. Okay, the recursion especially, you will see that some of these actually can be faster than the other, but you pay a price of some of the stuff as you will see. Okay, so once you know that there are all these differences and similarity, then you know that you have all these alternatives. You have to choose the correct one to use. On the other hand, if you do not know of their existence, then you may have no choice but to use one of them, only that one. By the way, for our assessments, as in tests, midterm, practical exams, and final exam, we at time will have to dictate the abstract data type for you to use. Basically, we will restrict your use of, for example, if we don't want you to use dictionary, we will state it explicitly. Otherwise, if we don't say anything, you are free to use whatever you want. Okay, so now remember these three keywords, the similarity, difference, and the possibilities. Okay, let's do the first one, the easier one first. Okay, so tuple is immutable, list is mutable. So I need to work with you. Okay, here is what I have. Let me just get you guys to help me. 黄可
Yes.
可琪呀，可琪。
Yeah.
Okay. All right. So here is what you see. X is this. So X is a tuple. Is that okay?
Yeah.
Okay. What is Y then?
The list.
It's a list. What is the list looks like? Maybe we can see it. X looks like this. And Y it's with two pointer pointing to this guy. Okay?
Mm.
All right. Print X1.
Two.
We get 2. All right.
Sorry. Can you ask someone else outside?
Sorry. I asked someone else. You are outside. What do you mean? You cannot see? Or what?
Outside.
Can you see? Okay, I get someone else. Schmidt.
Yes, sir.
Okay, so X1 equal to B. Is this okay? X1 is this guy too.
No,
No, why?
the tuples are immutable.
Sorry?
A tuple is immutable. It cannot
Yes.
change.
Okay, you cannot change any of them. Okay, any of the entries it's not changeable. Okay, so you're right. So there's an error. Tuple object does not support item assignment. Okay, so this is not allowed. So I have to do this. Is that okay? I want to change the 2 to B, so I have no choice but to change this. Is that okay for you?
Sorry?
So I want to change the middle guy. I want to change this guy to B. So I do this. Okay, what happened to this picture?
The middle guy will the X will point to a different memory location, right?
Okay, and what happened to this guy?
Yeah, the 1 to 3 will still stay the same.
Oh, why?
I thought because it's immutable, so it won't change.
It won't
just point
change,
to
yes.
different.
But why would it still remain there? X has been pointing to someone else. Why should this guy be
okay.
remain?
Yeah,
Huh?
now we'll point to the middle value will be B.
Sorry?
The
Yeah,
middle
the
guy
middle
will
value.
be B.
Okay,
Yeah.
why this guy remain there?
Because Y is still pointing to X, like the
Correct.
original value of X.
Yes, so this guy is still useful because Y has somebody that pointing to him, somebody pointing to him. So this guy is still maintained as it was.
Yeah.
If no one is pointing to him, what happened to him?
The memory will be like destroyed and can be used for something else.
Okay, that's very good. So if nobody is pointing to him, for example, if I don't have this guy, I only have X is 1, 2.
Mm.
All right. If I do this, the guy was gone. Okay, 1, 2, 3 is gone because nobody needed him. Okay, so that's why that becomes a garbage and it's being destroyed. Okay, so when I print Y, what happened, Ashmit?
When you print Y, it's gonna return 1, 2, 3, 1, 2, 3.
1, 2, 3, 1, 2, 3. Okay, I print X count 3. All right, now we need to see. We don't know what count, so we need to refer here. Count means return the number of times a specific value occurs in a tuple. So count 3, how many?
1.
1. Okay, because there's only 1 3 in there.
Yeah.
X dot index 3. Index means search the tuple for a specific value and return the position where it was found. So what do you get?
2.
2, because 1, 2, 3. 3 is at position 2 as indicated here.
Yeah.
Good. Index B.
1.
Index B. 1. Yeah. Correct. I pointed at the wrong place. It was supposed to be here.
Yeah.
1. What happens if I do this? Print X index 2.
I think it'll give you like an error because
Yeah,
it doesn't
it's an
exist.
error. Okay, let's try. If I try this, it's an error because tuple index X is not in tuple. Actually, this kind of error could be caught. Subsequently, you will see those exception. You can use it to catch it and then do something about it. Okay, but now here I don't do it. Okay, I just need to comment it out. Okay, thank you, Ashmi.
No worries.
Okay, let me try another guy. Chen He. Chen He.
No, Prof.
Hi. X is this. So what is X?
X is a list of 1, 2, 3.
Okay, X is a list of 1, 2, 3. Not yet. Okay, X is a list of 1, 2, 3. Y is XX. So
So Y is the first X is the original list. So it's a list in so it's 2 lists in the list.
okay. So these 2 pointer we have to change, right?
Yeah.
Pointing down now. Correct?
Yes.
And then what happened to this guy?
I don't understand. Like
Because they are no longer useful. Nobody point to him.
oh, then it will
Then
just be thrown away.
we
We'll
thrown
just
away.
yeah.
Yeah, they'll be thrown away. This is now list. Okay.
Yes.
X1 equal to B. Is this possible now?
Yes.
Yes, because this is a
It's a
list.
list. Yes.
Okay, so it's a B. Print Y. What do you
It
get?
will be the list 1, 2, 3, then list 1, 2, 3.
Okay. 1B3.
Oh, 1, 3, yes. Sorry.
Okay. Y00 equal to C.
Can it'll be 1.
Y00. This
Yeah.
becomes C. What
Yes.
is this bracket there?
Is a tuple. Oh, I don't think it works because cannot equate a tuple to the value.
Cannot? There's no error. It's okay. Just
Can.
that the parenthesis is useless.
Okay.
Okay, you can try. You want the tuple, you put a comma.
Okay.
Let's try. Yeah,
Mm-hmm.
let's go through the tuple.
Yes.
Okay.
So like
Then
by doing
print.
this, replace, right? Replace the original one will be replaced with the new C, the
Yeah.
brackets.
Yeah.
Okay.
Okay. If you don't want, we can change it back.
Okay.
This parenthesis is useless.
Mm. Yeah. Okay.
Print Y.
So Y would be the CB3 and the CB3. Yeah.
Okay. Print X.
Print X will be the CB3. One this only.
Okay. So we are here.
The
We're
W?
here.
Yes.
W, Y, Y.
Yes.
What do we have?
So it'll be the CB3 times 2.
Not so directly. It should be pointing to the Y, Y. Okay. All right. And it will be quite different from the Y, which
Yeah.
is CB3, CB3. When you print it, we change it to blank, empty
Yeah.
list. Print X, we got CB3. Print
Yes.
Y, we got an
Blank
empty in this. Print W, what do you get?
blank CB3 and blank CB3.
Oh, it's more than that. It's a tuple, another tuple. You're copying the whole thing inside. Copying the whole thing inside. You see the difference? Okay, let me
Uh,
just put in another one to make it clear. We are here. All right.
yes.
It looks like this. If you print it out, you will see it's different from the Y because another layer of tuple. Okay.
Wait, but the
Okay.
things are square brackets, right? So
Yeah.
is it tuple? They are tuple?
This
Eh,
list.
List of
Sorry.
this. Okay.
List. Sorry.
Okay.
Okay. So this one we had it. This one. This one.
Okay.
This one. What about this?
Y0 append A. So at the start, at the blank, you'll insert a new list A, just A itself, before the blank.
Okay. What happened to Y?
Y will become A, A comma blank comma CB3. So it'll be 3 lists in one list.
You see this Y equal to this?
Yes.
Yeah. What does it mean? It's taking the result of this guy, give it to
And add.
Y.
Yeah.
Yeah. But we got none.
Yeah.
Yeah. Why is it get none? Because append, it's add
Oh.
an element at the end of the list. It doesn't return anything.
Oh. Yeah.
When you clear, it remove everything in the list, it doesn't return anything.
Okay.
When
Only
it
the plot.
return,
Only
sorry.
the plot will return the number.
Yeah, so this one
Okay.
pop will return the number.
Mm.
I think this one also return the number. Remove the item with a specific value. Okay.
Okay.
All
Understand.
right, you have to try this. So this case is a trick. You get
Yeah.
none. Okay. What you actually wanted is this only. You don't want this. Usually, you don't want
Yeah.
this. Okay, you only want this. That means you only want this part. By itself, you
Correct.
already mutate it.
Mm.
Okay. So we are here. We wanted to add a A at the back. We added
Yes.
it without changing the Y. Okay.
Yeah.
When you print the Y, you get what you wanted. Print the W also got affected.
Sorry. Can I
Okay.
check? The blank one, right, will be replaced by the A because of the append.
This one?
Yeah, because initially the Y was a blank, then the CB3. Then when you put the append A, right, the blank list disappeared. Is that
Correct.
correct?
Correct. We can then go back.
Yeah.
Empty list.
Mm.
This empty list, this will be a A here.
Oh,
A. Okay.
so this append just replaces the empty list. Am I right to say that?
Yeah. I mean, it just added to an empty list. Well,
Oh,
we can do this one more time.
okay.
Y0 dot append another one.
Mm.
We'll see two of them. Right here. Got the A,
Okay.
got the B. All right.
Okay. So
If it
you'll
is
add on.
empty, you just add
Yeah.
one, add another one. Okay.
So for empty list, the append function just adds on to the empty list to give it the value,
Correct.
whatever.
Yeah. Empty means there's nothing there. I'm just
Okay.
adding
So
one.
so if the list is filled, let's say I append y1 append a, right? It will add on, you'll continue on. So there'll be a third list. Am I right to
Correct.
say that?
Yeah.
Okay.
We can do it just like that. Okay.
Okay.
Print Y, print W. Okay. Next. S is this. S is a list.
Yes.
S is a list. Now you see S dot append 5. What do you get?
1, 2. You get nothing.
Huh?
Eh?
Oh, yeah. You mean you print nothing. Print nothing, but you change the S to
Yeah. Correct. Yeah, the list will change, but the result will be none.
none. Okay, good.
Yeah.
Remove 3.
The result will be none also, but it will remove the number. Yeah.
Yeah.
It will remove that number.
Remove 10. Okay, so remove also doesn't give you anything. Pop is the only one that give
Yeah,
you.
pop is the only one that gives. The rest are the same.
Reverse the order. I see. Okay, pop is the different one.
Yeah.
Okay, none. Okay, next. Insert one position. Insert.
Yeah.
Add an element at a specific position.
So at the
So
second position, it will add in 11.
11. Okay, what
Yeah.
happened to the rest?
I think it will retain. So it will be 1.
Huh? It'll be
Mm,
1 and
it will be 1, 2. No, it will be 1, 11, 2, 4, 5.
okay, very good.
Okay.
Next. Insert
Uh,
10.
I think if I'm not wrong, it will add to the last at the end
Yeah,
of
to the
the
last.
yeah. The
Very good.
Pop
Okay.
0 will return 1, the number 1.
Or return 1.
Yes.
1. Pop minus 1.
It will return the colon 99, not colon, the double
String.
comma. Yeah, the string.
Pop
But it will return the 5.
5. Okay. Just one note here. Pop 0, if you check it out, it actually is O of n. Pop minus 1 and pop nothing, this means minus 1. It's O of 1. Okay. Why this is so, I asked in the forum. Okay, so you can check it out. All right, so this is the first part. You're working with tuple versus the list. You can see the similarity and the differences here. Next, we needed to work with tuple and list in functions. All right, when you work with functions, you're actually passing things into the function. So in passing things into the function, as I said, you need to know what are the various possibilities. In this case, the possibilities of passing values into functions are call by value, call by reference, and call by object reference. This is Python. This is not Python, but I mentioned it here because you needed to know that all the various possibility, even though this possibility does not exist in Python, but it exists in other languages. Okay, so when you're using a language, when you are, for example, C++ or Java, you have to understand that which way of passing parameters it's used by the system. For Python, it's this. Now, there's this web page that you should read yourself, all right, to know the difference among the three of them. Okay, what you have learned so far, it's this one. In the case of immutable like tuple and string, so you just pass them by values. That will do. Or number also the same. Okay, number, tuple, and string are like that. On the other hand, I must say that tuple actually it's more like the object reference also, but because it's immutable, it doesn't matter which one you're talking about. All right. So when you're reading this, take note of pass by reference, which is the second one. This thing doesn't exist in Python. It just gives you an illustration. In this case of pass by reference, this box is the box to keep the variable. Okay, in this case, the variable is called list and list. There's only one box. If you look at Python, pass by object, there are two boxes. Okay, there are two boxes for the same thing. When you pass this thing into here, they have two copies of it. One original, the other one is a copy. But both of them are pointing to the same object. Okay, the pointer it's in the reverse order, but you should see that it's pointing here and pointing here. So this is an object pointed to by this and this, the same. But passed by reference, there is only one box. Okay, so and the object is whenever you change the object, both of them are got affected. On the other hand, pass by object reference, when you change this, you may not affect the other guy over here because they are two different things. Pass by value it's a simple one. You just have two copies of everything. All right, it's one copy, one copy. Here it's two copies but one object. Here it's one copy, one object. Okay, so that's the difference among the three guys. This one is two copy, two objects. This one is one copy, one object. This one is two copies, one objects. Okay, you can write that down yourself, or you can review the recording to see that. This one you need very careful reading to understand this. For me, let me just give you some illustration here. Okay, let's do this. Brian Chung.
Yes, bro.
Brian Chung. Hi. Okay.
Hello.
I have a function this a equal to 10. When I say fa, I'm calling this function, right?
Yeah.
Okay. So what is x now?
A.
A. X is a, and x will get the value of a which is 10,
Yes.
correct? All right, and
Yes.
this is call by value because it's a number. It just give you the number. There are two copies here. Okay, next. X is changed to new. What happened to this picture?
The X gets replaced with the string new.
Okay, good. What happened to A? Any change to it?
No.
No. Okay, so when you return, when you print A, what do you get?
10.
10. Okay, good. Next. X is a string also. FA, what happened?
X becomes X string XYZ.
Okay. Now I change X to new. What happened to A?
Nothing happens to A.
Good. Nothing happens to A. When you return, when you print A, you got XYZ still. Next. A is a tuple now. Tuple, huh? What happened to X?
X gets replaced by a tuple.
Yeah.
The tuple.
Yeah. Okay. So this is called by object. So maybe I should put tuple here. So I should see this. 2 pointer, all right, and 1 object. That's what I meant. 2 pointer, 1 object. Okay, passed by object reference. All right, it means that the object, its reference are passed by the value. This is a short form for, it means object references are passed by value. All right. Okay. So now you see 2 pointer, that means 2 variable, 1 object. Now X is changed to new. What happened to this picture?
The X will get replaced to the string new.
Okay. And anything to do with A?
No.
No. So when you return, when you print A remains. All right. Next. This is another function now. A is a tuple. A is 10, 20 before and on the top. Now I change it to A equal to 10, 30. It will just be another tuple. B equal to A. What happened?
B will also point to the tuple.
Good. Next, GB.
So X gets replaced by the tuple.
X got replaced by the tuple. Or you should say that it's created a pointer from X to it.
Yeah, correct. Yeah.
Okay. Next, print ID A. This is the address of A. It's some number. It's the address. Is the address of A the same as the address of X?
Yes.
Yes. Now X is changed to 1040.
Yeah, it will point to a new tuple.
Okay. Print ID of X will be different from the before. ID of A and X, are they the same?
No.
No. Okay. And you return. You print A. A remains as 1030, right?
Yes.
Address of A and B remains the same. Okay. So this is again passed by object reference. So the A is actually passed in there, but it doesn't change. Whatever you change to X, it doesn't affect the A. Another one. Let's try this one. Okay, let me call another guy. Cohen Lim.
Yes.
Yes. Okay. X is a, Y is a, Z is a. What do I have? X is a, Y is a, Z is a. It's a list. Okay. Now I call f x, y, z. Come in here. So what is x1?
X1 is list of A.
A. And y1 is also A. Z1 is A. They are all three different A's. Okay. X1 append 2. What happened?
Then X will have A and 2 inside the list.
Okay. You see any change to the X and the X1 is changed. So it's X, correct? That 2 pointer, 1 object. So actually when you return afterward, you print X1, you get A2, you print X, which is the outside X, you also get A2. Correct?
Yeah.
Next, Y1 equal to A22. Y1 is here. So what do you do?
Y1 points to a new list A and 2, but Y, the original Y does not get changed.
Okay, good. Now you see that if you use the function append 2, it is modifying the original one. If you make an assignment, you are actually creating a new one. Okay, so the original y is not changed, but the y1 inside the function is changed. Okay. Next, this one, z1 append 2.
Okay, Z1 append 2 will change Z to become A over 2, and then Z1 will be assigned to that new list. So they will both be the same, but it's kind of different though, in the order that is done. They'll
Oh
both
no,
become.
this is the trick. This trick that we did. Z1 append 2 returns what? Nothing.
Oh yeah.
Okay, so you get none. And the original Z has the 2. So Z1 get none, Z has the A2.
Oh
Okay,
yeah.
catch up. Be careful. This kind of thing happen often in midterm, just to catch, to make sure that you are careful. Okay, so now you see the differences among them and among the X, Y, and Z. Even though you do things, so have to be careful. All right. And I needed to do the last part. The last part is the recursion with tuple and list. All right, I'm going to use an example. My example is to multiply all the numbers in a sequence, which is the tuple or the list. So here's the code. All right, multiplying all the numbers in the tuple in a recursive manner. So this is the code. If the tuple is empty, I return 0. If the tuple has only one item, I return that item. Otherwise, I take out the first item, multiply with the remaining item. All right, so let's see if the tuple exists. Let's see, this is 1 times 3 times 5 times 1 times 3 times 5. I should get 225. I get 225. Okay, so let's see the code. The code looks like this. Okay, at this stage, let me call up Isaac Lam. Hey, did you come yesterday? Let me try another one.
Hello. No, I didn't come yesterday.
Okay, Isaac then. Then it must be another guy. All right, so from this picture, what do you see?
So the function calls the tuple and then takes out the first element every time, all the way until it gets only one.
Yeah.
Then it should go, if it's 1, it returns just that value and then starts multiplying it with the previous one that was taken out.
Okay, so you are telling me this. Okay, the answer is then 225. Okay, I stop here and tell me what is the time complexity.
Like at the overall function, or
The overall function.
is the iteration considered ON already? Like to
Where?
when you do the recursive call and then you have to make a new tuple with the bracket 1 to the end of it.
Yeah.
If
How
that
much
is
time you're
ON.
asking to get from here to here?
Yeah, because
Yeah. How much time?
ON, I think, for each
N
tuple.
minus 1, right?
Yeah.
You have to take out this guy and pay for copying.
Yeah.
So you pay ON time. ON minus 1. What about this one?
The ON minus 2,
ON minus 2. This one.
minus 3.
Minus 3, minus 4 until 1. Correct?
Yeah.
So you're paying constant to check, but then you need to stack up this number and call the product tuple again with this new tuple. And to create this new tuple, you pay the time of the length of the t. Okay, so you have 0, you add 1 plus 2 plus 3 plus 4 plus 5 until n minus 1. As a result, this whole thing is what?
ON squared.
ON squared. Very good. So this is ON squared. What about the space?
Space would be is it also ON squared?
Yes, because the space is exactly what you're seeing. All right? You cannot ignore any one of these guys. These are the spaces. All right? Ray Yang.
Yes.
Okay, are you
Yes.
okay now?
Yeah, but I'll just take time to digest lah.
Yeah, okay. So this is why it is n squared here. Because this simple statement require you to make a copy of this guy. This is called slicing. This slicing takes n minus 1 time. And n minus 1 time, n minus 1, n minus 2, n minus 3, and so on. You add them up, you get n squared. Okay. Isaac, what is the space? Because of this, all these are actually the space. And you can see that the time can never be larger than this, can never be smaller than the space. Because you need this small space, you better have this amount of time to use them. All right. So this is one possibility. Okay, one possibility because we use tuple. What if we choose to use, instead of tuple, we use list? Let's say we use list. Okay. Let me copy my list. Okay, here, product using the list. I call the list and I do this and same example, and then let's see. This is the original list. Any difference? Let's try. Darius. Darius. Hello? Cannot hear you. Yeah, let's try another guy. Jiren. Jiren. Are you there?
Hello?
Yeah, louder. Okay.
Can you hear me?
Yeah, can hear you, but louder. Okay. From here, what do you see? If we want to understand the time and space complexity.
It works similar to the non-list version.
Yeah, it works similar to the tuple version. So any change to the time and space? Yeah, children.
Uh, I
Only, huh?
don't think so.
Yeah, you're right. You don't think so because this is again, you are creating a new list. All right, you're slicing to get the new list. So you get the original list, you slice it, slice it, slice it, slice it, slice it. So you are adding 1 plus 2 plus 3 plus 4 until n minus 1. And therefore, this is also n squared. And the space is also n squared. All right, so this is kind of stupid that we have a list. We know that we can actually modify the list without creating new list. This is creating a new list. All right, so let's see the version 3. This is my version 3. Okay, version 3 here. Here is my list. I'm going to call it. So the execution looks like this. Okay, let's try. Leon. Leon.
Hi, hi, Prof.
Hi. From here, what do you see? If it is empty list, I return 0. If it is one item, I just take the item and return it. Otherwise, I take the last item and I multiply with the list. This T, because of this T, pop up. So this T has one less element, okay, for the recursion. And it looks like this, the recursion. What do you find here then? Leon?
Yes,
Okay, let
all
me
links
back.
to the same list.
That is backward. Okay, forward. You see, I take out the 5. I take out the 3. I take out the 1. Take out the 5. Take out the 3. Take out the 1. And then I multiply, I get value. I still get 225. You see it? Okay, so do I achieve the goal of getting the product?
But still the
Right?
same product. Yeah.
Yes. And then what do I get for my time and space?
I think space is O of n,
Why?
because you just use back the same list. You're not creating like new
Yeah,
list.
but then where is the n coming from then?
N is the original length of the list.
Yeah, but this one give you for free. This original is not counted.
Oh,
So where is this n coming from? You're correct, O of n. This come from where? Stacking up the multiplication.
oh,
Or the defer multiplication. Okay? What about time?
time is just O n, I think, as well, because of the recursion.
Yeah. Okay. All right. So both are ON.
Okay.
Okay. Here we have to use pop -1 because pop n is linear. All right. So we don't want to pay this linear. We want this to be constant. right? If you use pop 0, then this whole thing will change again, will be n squared. Okay, now what's the problem with this version? I have another version, last one. So I'm giving you all the possibilities. What's the problem with this way of doing things? You got your answer, all right? But you destroy the list. Okay, Leon?
Yeah.
This is what we don't like. We don't like side effect. Okay, this is like taking medication, we don't like side effect. All right? Side effect of destroying the input list. Okay, so this is usually not allowed. And so we need to have the last version. And last week, we talked about inert function, and we want to use the inert function because we want to hide things. So we hide this helper within here. This is doing the thing for us. And we make a copy first and destroy the copy along the way without touching the original T. So, okay, so this is my last version. Let's see. Okay, so this is the last version. So you are inside the function, you make a copy. So this is a copy. And then now you call the helper. Then the helper is needed because I want to do recursion in here. You see the helper is destroying the list, but the original list remains. At the end of it, I got the answer, and my list remains. Okay, I'm done. All right, so this is what are the various versions. You're seeing all the possibilities. And what I'm doing today is what you should be doing yourself so that you can then address some of possibly my exam questions, which I'm learning from here to set those questions for you. All right, I'm done here. Any question? You okay? Give me a check if you're okay. All right, I will post all this code in next to my review. That means I'll put it here. I'll put it in here so that you can download and try it out yourself, all right, or for your own reference. There are for sure much more that you can learn yourself other than these few examples that I'm giving you. You should try other things, all right? And you see that the certain things are counterintuitive. Of course, if it is too much of a counterintuitive, it's too specific, it shouldn't be fair for me to test you. Okay, otherwise, but you should at least make clear what all these guys are. Okay, if not, I will pass on to give me a check that I can know that you are okay, and I can hand over to Junjie. Okay, thank you. So I will not follow you guys. I'll leave Junjie to do the tutorial, and he should be starting at 8 o'clock. Junjie, can you say something?
Okay, can you hear me?
Yeah. Okay, I make you host. Now you're taking over.
Yeah, okay.
Okay, I will leave today. Bye bye, guys. Happy New Year.
Right, guys, I'll start at 8 p.m. Feel free to take a break. Alright, hi everybody, welcome back. So the time now is 8 p.m. I'll begin the tutorial now. This week's tutorial is tutorial 3 on recursion, iteration, and orders of group. So the first question is on drawing the tree representing the process generated by counting change. So counting change is the function you were taught in lecture. So for the specific situation of 11 cents with our 5 denominations, 1 cent to 50 cents. So I hope you guys actually took the time to draw out the tree. So it's a good way to understand how counting change works. So can I have some of your answers? I want to see some of how y'all drew it. I'll show you my answer later, but I'll give you guys 1 minute. Can you like take a picture or send it in the chat? We can go through your solutions. It looks like we have no submissions. Well, oh wait, we got one. All right, let's see. All right, so let's see who sent this. Okay, thank you, Yanshu. So this roughly shows the tracing of the output. So we start off at 11 for the amount. There you go. It looks like you're trying to use 10 cents and you're counting how many ways there are to count 10 cents with using the 10 cents. So you count off 10 cents, remove from the amount, you left 1 cent, and you can only count that using 1 cent. So this is a total of 1 way to count 11 cents using a 10-cent coin and a 1 cent coin. And over here you show another way, or using 5-cent coins. So you can use a 5 cent, and then you can use another 5 cent and a 1 cent, and that's another way. Another way is using all 1 cents, while you're actually missing quite a few ways of counting. And it's also good to show the ways that aren't counted, like to like show the situations where it will lead to 0. So let's see how is it. So before we continue, let's just briefly go through counting change to make sure you guys understand. So we take in 2 inputs, amount and denominations. So how many denominations there are? By default is 5 because we define 5 denominations that we're looking at for coins. Now, these are the base cases for the recursive functions. If amount is equal to 0, we have successfully counted one correct way of counting the change using some number of coins. Else, if the amount is negative, we have taken off too much. So that's not a valid way of counting. That's why it adds 0 to the total number of ways we can count the change. Else, if denomination is equal to 0, this is also invalid because we have no possible coins we could use to count. So we will return 0 in this case. Else, we will return 2 branching paths of calls to counting change. So the left call represents what happens if we were to actually count one of the coins, the biggest denomination coin. So if we start at d equals 5, the biggest denomination coin is 50. So we'll try to minus off amount by 50. And then we'll continue counting how many ways there are after we have taken off 50 cents. The next way is if we don't use the biggest denomination, then we'll just minus out the d by 1, and we'll pass it in to the next call of the function. So I'll show you how the tree should look like. All right. All right, I need to zoom out this. All right, here we go. Okay, this shows all the invalid calls also, the invalid ways of counting. So let me get. Okay, I've shown the left calls and the right call. So we start off at CC 11 cents and 5 denominations. For the left call, as you can see from how the function is written, we'll try to minus off 50 cents. And when we minus off 50 cents, we will see that the remaining amount is already negative. So this is an invalid way of counting 11 cents because we cannot have any ways where we like count using a 50-cent coin. So that's why we add 0 to the total count. And the function ends here. We do not have more recursive calls because we already reached an invalid way of counting. So then the right side call is when we minus off the denomination by 1 and we recall it. So recall counting change with 11 cents and 4 possible denominations. So now we'll try on our left call to minus off 20 cents. Minus off 20 cents, we'll be left with negative amount. That's why this is an invalid way of counting. We add 0. Now for the right call is counting change 11 and 3. So 11 and 3, which means the biggest denomination we have is 10 cents. So 10 cents is actually a valid way of counting. We can take off 10 cents and we still have amount left. So we have to keep continuing calling. So again, we try to minus off 10 cents again, find that we have left with a negative amount, and this is an invalid way of counting. That's why I add 0 to the count. Next on, we try to minus off the denomination. So we go down to the biggest denomination is 5 cents. So now we try to minus off 5 cents, cannot. So that is not counted. Now we go on to our last denomination, 1 cent. We only have 1 cent. We try to minus off 1 cent, and yes, we are left with amount equals to 0, which means we are done counting this whole path. So this entire path is one valid way of counting, where we use a 10-cent coin and a 1-cent coin. This are one valid way so far. So now we try again on the right side. This right side call counting change 1 with 0 denominations. There are of course 0 ways of counting 1 cent with no coins. So that's why this is an invalid way where we add 0. Now we go back up here to the next subtree for counting change 11 and 2. So notice that over here we have not actually minus off a 10 cent. We have not used a 10 cents. This is a different path where the biggest denomination is 5 cents. So we try to minus off 5 cents. Yeah, we're left with 6 cents, and so on and so forth. We have a few different other ways, other valid ways. This path is where we use 5 cent, 5 cent, and 1 cent. This is another valid path. The other valid paths are the other base cases where we add 0 to the count. When we add 1 is when we actually found a correct path. Yep. So I hope this actually helps you understand how exactly counting change works. It's quite a complicated tree recursive function. But once you understand it, it's quite cool. Okay, let me see. Any questions so far about counting change? If not, let's move on to the next question. What are the orders of growth and space? Or what are the orders of growth of the space and the number of steps, which basically means the time complexity for this process as the amount to be changed increases. So what are the time and space complexities relative to amount? Can I get some answers? If not, I just like choose someone. Okay, let's have Olivia. What is the time and space complexity of counting change?
Hi, can you hear me?
Yep.
Okay, but for this specific question, I don't think I was really very sure about. I don't think I was really sure about it lah. Yeah, but
No, it's fine. You can just give it a try. Imagine this exam scenario and like your task to answer the time and space and also give an explanation as to why.
I think okay for space, right? Since the number of variables are only constrained as such, like the number of denominations. So I just chose ON because the number of variables wouldn't increase exponentially. That's what I chose. Yeah. But
Correct.
for the number of steps, I think from my observation, okay, this is a quite a rough guess, but the number of steps would just increase exponentially by to the power of 2 to the power of something, because yeah, every recursive function will split into another 2 functions, another 2 possibilities. Yeah, that's why I chose 2 to the power of n.
Right, thank you. So you got the main idea. You're correct in saying that the time is 2 to the power of n, and space is On. But for the explanation of space complexity, I'll show you the ideal way of explaining for this type of exponential functions. So let me just copy from my slides. So by the way, there's a structure to answering this kind of question. So usually in the exam, they'll ask for time complexity. Sometimes they'll mention something it is related to. Like for this question, it's asking for time complexity relative to amount. So when you say On is it just means that n refers to amount. But sometimes the question will just ask like time complexity in general. So when you write On, you should mention what n refers to. Sometimes it's like the size of the tuple that is input or the length of the string that is input. So you must like mention it if n is not immediately apparent what n refers to. So time is 2 to the power of n, where n is amount. The reason why, the explanation is as the number of recursive calls doubles or increases by a multiplicative factor of 2 for each increment of amount by 1 in the worst case. So to illustrate this, I'll use a simpler example of Fibonacci. Okay, the naive Fibonacci implementation, the one with 2 recursive calls. Because that's easier to see like how it changes. Let me get a blank space to work with. Right, let's say we start off with Fib 5. Let me move it down. Naturally, it will call Fib 4 and Fib 3. Fib call will call Fib 3 and Fib 2. Fib 3 calls Fib 2 and Fib 1. I'll put it just as 1 because this is a base case. Now this calls 1 and 0. This calls 1 and 0. This calls Fib 2. This is a base case. This is a base case, and this is a base case. So you notice that, look, there's a tree-like structure in the recursive call pattern. So if you draw out the calls, it looks like a tree. Now, notice what happens if you were to call Fib 6 instead. So if you increase the input n by 1, Fib 6, notice that what you're doing here is Fib 6 will have to call Fib 5 and also Fib 4. So Fib 4, you know it has to call Fib 3, Fib 2. This calls Fib 2. This is a base case, base case, base case, and so on. So you can see that roughly the size of the tree that represents the calls has roughly doubled. So it's not exactly 2, but you can say that the number of steps is bounded by 2 to the power of n, where n is the input size. So when you increase the input from 5 to 6, basically increases n by 1, you're increasing the number of steps by up to 2. So if you've read up about this, the the exact constant is actually the golden ratio raised to the power of n. But for the purposes of this course, you can just understand it as the time complexity of the naive implementation of Fibonacci to be 2 to the power of n. So it's the same thing for counting change. The counting change, even though it has 2 inputs, it also, when it scales according to amount, if you increase amount by 1, it causes this tree structure to double the same way as Fibonacci, from Fib 5 to Fib 6, or from Fib n to Fib n plus 1. So from this, you can visualize that the number of steps or the total time taken will roughly double for each 1 unit increase in the input n. Now for space complexity. So space complexity, so Olivia, you said you did not give the accurate explanation for exponential functions, but that's okay. We can learn and we can learn the correct answer and explanation for exam. So let me get it from my slides. The space is ON. This is the same thing for Fibonacci. Now, the space is ON where n is amount, because that is the maximum size of the recursive call stack. So this is the same explanation for why counting change has a space complexity of ON and why Fib has a space complexity of ON. So I'll illustrate to you why. So you notice when, let's say, an exponential function like Fib is called, it has 2 different paths where it can go. So like this is the left subtree, this is the right subtree, referring to this part and this part. So how Python works is when it evaluates like the left side call, it will evaluate this in full before it moves on to the right side. So over here, Fib 6 will first have to evaluate Fib 5. But when it evaluates Fib 5, it has to evaluate these two, right? But it will only work on this first. And it will ignore this for now. But then when it calculates Fib 4, it will have to calculate Fib 3 first, because that's on the left. And so on until the base cases. Now, once it has calculated this value, it can pass it on to this, and then it will calculate this value. But by then, it will have cleared up the space on the recursive call stack, on the stack. So this space is no longer being used. This space is no longer being used. Now, once it has the answer for this, it can calculate this, and then it can clear up the space and go up. So it will calculate the entire left subtree, then it will clear the space, and then it will work on the right subtree. So you notice that the space taken up by the program is not going to be 2 to the power of n. It's going to be ON. So why ON? ON is the largest size of the recursive call stack. So if you look at it in Python tutor, you'll notice that the most number of deferred operations is roughly equals to n. So it will defer the calculation for Fib 6, Fib 5, Fib 4, Fib 3, and Fib 2. Calculate these, and it will cascade upwards. So notice that throughout the entire evaluation of this expression, Fib 6 or Fib n, the maximum size of the recursive call stack or number of deferred operations that Python is keeping track of is no more than 6 or n, or roughly 6 or roughly n. So relative to the input, the maximum size of the recursive call stack is n. So that's why space complexity is ON. Right, any questions so far? This is a standard answer for these kind of questions. So whenever you have a exponential function that looks roughly like this or roughly like that, these are the explanations as to why the time is exponential and space is linear. All right, let's move on. Okay, for question 2. Question 2, a function is defined by this above. Write a function that computes Fn by means of a recursive process. So basically, they want a recursive solution for Fn. Can I get your answers in the chat? Thanks for answers. For this part, there is only really one way to do it. So you notice that this function, this mathematical function, is a piecewise function where we have one case where when n is less than 3, we have to return n. And when n is more than or equals to 3, we return this recursive calls, 3 recursive calls. So this is very similar to how we write functions in Python. So like we need to convert the math to code. So for the recursive solution, it's very simple. It's basically the exact same thing. Piecewise functions and recursive functions are very similar. So if n is less than 3, just return n, else return these calls. So let's have Yanqing, you answered time complexity equals to 3 to the power of n, and space complexity is equals to O(n). Can you explain why?
For time complexity, it's basically like as like n increases by 1, like it splits into the 3 branches fn minus 1, fn minus 2, and fn minus 3. So like it's like times 3. So it's 3 to the power of n. So space complexity is like for length of the tree is from 1 to n. So I think it's like, so it's just on. I think.
Okay, thanks. So yep, those explanations are roughly correct, but for exams you can just like write this standard answer. So time complexity is 3 to the power of n, as the number of recursive calls, wait, actually you should say that f calls itself recursively 3 times. So the number of recursive calls to f triples or increases by a multiplicative factor of 3 for each increment or amount by 1 in the worst case. You don't even have to say in the worst case, because big O notation already implies in the worst case. Now for space, ON is the same explanation, max size of the recursive call stack. So if you roughly draw out the tree structure, you can do the same for this question. Let's say 5. It will split off into F4, F3, F2. So this splits off into its base cases. Let's do it like this. So from fib 5, you already see it has a tree-like structure. If you call fib 6 instead, you'll notice that not only does it have to call fib 5, the entirety of fib 5, but also has to call the entirety of fib 4 and fib 3. So each of these roughly have a tree-like structure. But you can see that it's bounded roughly by 3 to the power of n in total. So that's why you can say that the number of recursive calls to f triples or increases by a multiplicative factor of 3 for each 1 unit increment in input n. And same thing for the maximum size of recursive call stack. So the space complexity is ON because the maximum number of deferred calls or the maximum size of recursive call stack is n. And nowhere else in the entire evaluation of the function will you ever have more than n deferred calls, more than about n. So you can say that space complexity is ON. All let's take a look at the iterative solutions. So let's see your iterative solutions. Oh yeah, the F2 doesn't branch out. It's a base case. Yeah, I'm looking through your solutions. A lot of you are doing it the same way. I'm trying to look for a very specific way of doing it so we can look at the alternatives. Right, it looks like most of you, actually all of you actually did it the optimal way. So I'll have to manually get out the suboptimal way for demonstration purposes, like learning purposes. I'm gonna go look for it. Okay, I got it here already. Let me just find the person who sent in this answer. Right, Yutao, can you explain your solution?
Hello.
Hello.
So I did conditional to get out the n less than 3 case first. Then afterwards, I did since Fibonacci starts 0, 1, 1, I did not Fibonacci, sorry, the term starts with uh 1, 2, and 3. So I did the one term and two, the first term, and I did the first, second, and third term first as 0, 1, 2. Then I use answer equals 0 to store the answer. Then I did the loop, which will change the terms prior to the current term in order to continue calculating for the answer.
Yeah, thank you. So what are the time and space complexities, and along with explanations?
The time should be O(n), where n is the size of the input. Since the number of times the loop is called is proportional to n. Then space is O1 since there are no deferred functions.
Yep, thank you. So yeah, On because the loop runs about n steps relative to input n. And space is O1, but O1 because of you have a constant number of variables that are keeping track of, 4 variables, and you are reassigning them. So you're not like using up all the space like 4 times n. You're only using 4 variables at a time, and each time you update them, you basically just like overwrite the value. So at most, you're keeping track of the space of only 4 variables, and this is constant relative to input n. That's why space is O1. All right. Okay. So none of you actually gave this type of answer where you actually build out a tuple. So this is a different way of doing it. So I'll just like run you through it. Oops. So we have the just a if statement to catch for when n is less than 3. So this very simply just returns n. But otherwise, we'll start off with a tuple of 0, 1, and 3. 0, 1, and 2 to keep track of 3 terms. Now we'll iterate through a for loop n minus 2 times, and we will add to the tuple 1 element. So this is how you concatenate tuples. So this itself is a tuple, and you're concatenating it to results. And what you're doing is you're taking the last element of the results tuple plus 2 times the second last element of the results tuple plus 3 times the third last element of the results tuple. So you notice that the results tuple is going to grow over time, over these iterations, and you're adding on elements using the current last, second last, and third last elements. So this is called dynamic programming. You'll learn in the future, but some of you may intuitively like think of these kind of solutions. So these are valid solutions also, but we'll look into the time and space complexities. So let's have Ruiyang, can you explain what the time and space complexities of this function is?
Wait, let me wait. Hang on. Is
Right.
it like wait, hang on, wait. Is it the space complexity is O1, then the time complexity is ON, is it?
Can you explain?
It's O1 because like it's just like just one value lah. Then for ON because it loops n times.
All right. Okay. So that is wrong, but I'll show you why. So we can all learn from this. So notice that we are keeping track of a results tuple. So this is not an input tuple. This is a tuple that we actually use during the operation. So results starts off like size 3 with 3 elements. But throughout this operation, throughout this for loop, we're actually concatenating elements to the result. So we have to keep track of more and more results depending on how many times you iterate through. And how many times you iterate through is relative to n. So the size of the results tuple is going to be 3 plus n minus 2, but we can just simplify it, is roughly n. So this results tuple is going to scale linearly with regards to the input n. So the maximum size of this results tuple at the end of this entire operation is going to be roughly n. So that's why space complexity must be n. If let's say the results tuple had been an input, that will change things because like space complexity is equals to the added space that the function needs. So this tuple that keeps track of the results is going to add to the space complexity because the maximum size of this tuple, the number of things you need to keep track of, is going to scale in proportion to the input n. And for time complexity, you're correct to say that this loop will iterate roughly n times, n iterations. It's actually n minus 2, but it's roughly n. For the sake of time complexity, is about n iterations. But this step over here, whatever is repeated per iteration, notice that this is tuple concatenation. So what this is doing is adding a tuple to this tuple. And remember, as you guys learned, that tuples are immutable. So there is no operation where you can just add one element to the back of a tuple, because that will be mutating it. That will be changing the value of a tuple. So tuples are immutable. They cannot be edited. What you can do, on the other hand, is actually reassigning the value of results. So this is how it looks like. So let's say results is currently pointing to a tuple with 3 elements. What you're doing here, this step, is you're taking result, the current value of result, let's say 3 elements, plus a tuple. So this makes it into a tuple with 4 elements. Then you're reassigning it. So results no longer points to this tuple with 3 elements. It is now pointing to this new tuple, which is made out of the original 3 elements plus the last element. And since no variable is keeping track of this tuple, this space is freed up. So that's how Python works. So now notice that this is a new tuple. So when we create a new tuple, how long will it take to create that tuple? It will take 1, 2, 3, 4. Basically scales in linearly with respect to the size of the tuple. So you guys actually need to notice the time taken for creating a new tuple is n relative to the size of the tuple. So if the size of the tuple is n elements, the time taken for that operation is on. So this is an on step. This is n operations. So n times n is on squared. It's same thing for like tuple slicing, string slicing. Let's say you had a tuple which is like 5 elements long, and you did this like let's say 2 onwards. This will take on time relative to the size of the tuple because you're creating a new tuple. So that will take like at worst n steps, n time, yeah. N squared. Okay. So I have some extra questions on time complexity for you. So I'll just get some people to answer. So take a look at this. Okay, Chen Yang, can you answer what is the time complexity of extra 1?
Is it on square?
Can you explain?
Because is it like because there's 2 for loop, right? So wait, no, is it because can I change my answer? Is it like
Yep.
Is it O1? Because step is like a storage, right? So every time you look through, you're storing it. So there's no additional.
Well, are you talking about space complexity?
Okay, no, that's space. I don't know. Is it? Yeah, is it n square? Because there's
All right,
2.
you almost got the right idea, but notice that there are 2 different inputs. So there's n and there's m. So you see, if I were to pass like,
Oh yeah.
okay, never mind, I'll just go through. So if I were to pass n equals to 10 and m equals to 20, look, we will get 200 because the number of steps, the number of time steps is incremented. So this is basically just, I'm illustrating you how many steps is actually taken through for this program, for this function. So there's a for loop that runs n times, and within that for loop, we have another for loop that runs m times. So notice that for all this, when n equals to 5 and m equals to 7, we have 35 steps in total. When n equals to 9 and m equals to 5, we have 45 steps in total. So what this is showing is that the number of steps or the time taken for this function scales linearly with respect to both n and m. So you cannot just say that the time complexity of this function is a function of only n. So if you were to say that it's a function of only n, like let's say you say it's n to the power of 2, you're saying that m does not affect the time taken by the function at all, and is only with respect to n, which is untrue. If you were to change the value of m, it does change the time taken by the function with respect to m. So exactly how many steps is taken is n times m. So this is also a possible type of time complexity question that comes out of exam. It's not just functions related to just n, where n is like a number, or n is a tuple, or n is a string of length m. It can be such that the question actually has a time complexity that is affected by two different things or more. So let's go on to the next question. This is a different kind. Okay, so let's have Darius. Okay, Darius, what is the time complexity of this function? Okay, I'll give you some time to read through it. Extra 2. Hi, Darius, are you there? Darius, you? Okay, now we can get Ayan Khalid. Ayan, are you there?
Hi, can you hear me?
Yep.
The time complexity will be O, the higher integer of n or m.
Yes, correct. So how you can write this in exam is like O maximum of n and m. So this is actually an expression that has come out in previous papers. So yes, the time taken by this program, this function, is not necessarily just related to n or just related to m. You notice that there's an if block here where if n is more than m, we'll have a for loop that iterates n times. But if not, if otherwise, if m is more than or equals to n, we have a for loop that iterates m times. So this is different. So the time taken or the number of steps is actually the maximum of n and m. So we can actually like demonstrate here. See, the total number of steps is actually the larger of both inputs. So yeah, time complexity is O maximum of n and m. So the same thing for this function. I basically just flipped it. So the time complexity of this is O minimum of n and m. All right, for extra 4, now the inputs are tuples instead of just numbers. So let's have a Cohen Lim. Can you answer what is the time complexity of this question, of this function, extra 4?
Can you hear me?
Yep.
Is it like the length of tuple 1 and 2?
So what's the expression?
Len top 1 plus len top 2.
Yes, correct. Okay, what you can write is O n plus m, where n is the length of tup 1 and m is the length of tup 2. So notice that the difference between these two, this function and the other function is, here we had a for loop within another for loop. So the total number of steps will be n times m here. But for here, we have two separate for loops, one that runs after the other. So first, we have the for loop that runs the number of steps relative to the size of tup 1. And over here, we have another for loop that runs afterwards that iterates m times, where m is the size of top 2. So you can write the time complexity as O(n) plus m. All right, since we have not much time, I'm going to skip the extra question 5. Okay, question 3. Write a function isFib that returns true if n is a Fibonacci number and false otherwise. So can I get your answers in the chat? Oops, I didn't see your chat message. Right, so Bruce, can you explain your solution and what the time and space complexities are?
Hello.
Hello.
So so this checks if first if n is less than 0, cause below 0 is not considered a Fibonacci number, so it will straight away return false. So next it will check n is less than 2. So this case will only pass if n is equal 1 or 2. Then it will return true because they are both Fibonacci numbers. Next, it will basically do the iterative approach of calculating the Fibonacci number. So if we are able to calculate a Fibonacci number that is equal to n, we will return true. If we go over n, means it's false. And if it's less than n, we will continue to calculate. The time for this approach will be O log n, because as we calculate the Fibonacci number, the Fibonacci number will increase exponentially, which means the number of steps will reduce logarithmically. For space will be O1 because the number of variables does not change.
Yep, thanks. So that's correct. So for visualization of why the time complexity is O log n, I actually look to this simpler solution. So this solution keeps track of 2 variables. So it's similar to this one above. So it iterates with a while loop also, while a is less than n. We'll replace the values similar to how we did the fib function above. And we will return at the end like whether a is equals to n. So let's see here. Notice that the loop stopping condition is when A is less than n. So A starts off being 0. So I'll draw a table actually. So A is a table of values of A. And I'll show the iteration number. So this is iter. At iteration 1, A will be replaced by 1. At iteration 2, A is replaced by, let's see, oh yeah, 2. Okay, then so on and so forth, 1, 2, 5, 8. Now notice that within the iteration, as like the iteration number I increases from 1 to 5, A actually increases faster. And you continue to increase faster and faster, like 13. And the value of A over the number of iterations increases exponentially. So you know the stopping condition is when A becomes more than n, right? But the number of iterations that it will take for A to reach n is not I, is actually like log I. Whereas here where you expect for a normal loop is I is over here. When n equals to I is a point over here, but since A is increasing exponentially, the time taken for A to reach n is logarithmic. So notice that. It's also similar for like types of questions where like binary search. I don't know if you all have reached binary search, but let's say for a question, let's say example n. Then we have A equals to 0, while A is less than n. A plus equals to A times equals 2. Actually, let's start at 1. And let's just like that, yeah. So the time complexity of this function is very similar. Time complexity of this example function is, look here, the stopping condition is when A is less than n for the for loop. So iteration number the value of A, which is the control variable for the loop, or otherwise known as like the counter, it grows exponentially over the iterations. So it's going to reach n very quickly. So let's say n had been equals to 100. It will only take 7 iterations for A to surpass n, and definitely not anywhere near 100. So exactly the time taken for this function at x is log to base 2 steps, which simplifies to log n. I'll show you the explanation for this later. All right, so now, so is log to base 2n equivalent to log to base 3n? So let's have Ashmit answer. So Ashmit, what do you think? Ashmit, are you there? Okay, if not, we can have Chishan. Chishan, are you there?
Yep.
All right, so based on how you feel, do you think they are equivalent?
Don't think so.
All right, why?
My guess is that like the rate of increase is different.
All right, So actually they are equivalent, but you're correct to say that the rate of increase is different. So when we have a time complexity that is represented by like log to base square n and log to base 3n, this basically refers to the fact if let's say the problem size is being halved at each time, so this is cut off, then it's cut off at each iteration we decrease the problem size by half. So the number of iterations is actually going to be like log n with respect to the input. And for log 3 is represented if like we have the whole problem and we 1/3 it at each iteration. But you'll see that these two expressions are actually equivalent in terms of big O time complexity. So let's see log 3 and we can use the change of base formula. So log 2n divided by log 2, 3. And you see that log 3n is basically log 3n is log 2n times a constant. 1 divided by log 2, 3 is actually a constant. So you know that in big O notation, you can like take out constant. So since this is a constant, these two are equivalent in terms of big O notation. So this is just for you all to understand why we write log n time complexities as just log n. So it does not matter what the base is. So that's why if like for our example function here, even though we times 2 the a at each iteration, and over here for is Fibonacci, the number of iterations is different relative to the input, but we can both say for these two functions that the time complexity is O log n. Okay, let's move on to the last question, question 4. Okay, so we call the taxi fare example given in lecture 2. So we had global variables keeping track of like the stage distances from when the different fares will kick in. The start fare is 3. They're all constants. We set them before we define the function. We have the increment per distance and we have blocks here. So what we don't like is the use of global variables. It makes it very restrictive. So like we want to define a function that can create an inner function. So make fare needs to take in all these inputs, the inputs that we originally had outside in the global space. And we want it to create another function that it returns that we can use to save to another variable. So let's say comfort fare is equal to make fare with all these inputs. It creates another function, like a fare function that takes in only distance, and you return the price for that journey. So let's see your answers. Right? Okay, Zhiyan, can you explain how your function works?
Okay, what I did was basically I took what was in the lecture, which was taxi fare, right? Then I returned it as a function without the parameter, so that if when I call comfort fare, I just need to input distance.
Yep, thank you. So yeah, this is the correct way of doing this question. So this question is a higher order function question. So a higher order function is basically a function that either takes in a function as its input or gives out a function as its output. So in this case, this is a higher order function that returns a function as its output. So these inputs are set by the makeFair function. When it is called, it defines another function inside it, taxiFair, that varies according to these inputs. These inputs will affect how the inner taxiFair function works, and this taxiFair function is returned. So, but it's returned as is. We return the function as is without calling it. So that when we save it to a variable, comfortFair, we save it to a call to makeFair. Inside comfortFair is basically the specific taxiFair we have configured according to the original inputs. So now this specific comfortFair function is going to take in distance and return a price based on the parameters we input to the old call to makeFair. Yep. Okay, so that's it for that question. I hope you guys understand. If anything you're unsure about, you can stay and ask questions, but I'll end the lesson here. It's 9:01 p.m. If y'all would like me to go through the extra questions, I can. The 1 week skip. Extra 5. If anybody want to try. Oh shit. Okay. What is the time and space complexity of extra 5? Okay, this one is actually very hard, so I won't subject somebody to answer if they don't know how. Anybody wants to try explaining, they can just raise their hand or start speaking. Just start speaking. Is it 2n plus 2m? Okay, no. Remember that tuple concatenation takes time also. You are creating a new tuple and reassigning it to result. So keep that in mind. Oh, Yansu says n squared plus m squared. Okay, you're very close. You're missing something. Is it len top 1 plus 2 squared? Okay, Ayan Khalid, you are correct. So can you explain the answer? And you want to try explaining? Yes, Yanqing, you are correct also. Ayan or Yanqing, you want to speak up and explain? Go through so we can evaluate your explanations.
Is it because each time you append is n plus m?
Alright, let's go through step by step. Okay, where are you talking about?
Basically, cause the just on the previous question, right, is n plus m, len of type 1 plus len of type 2. But for this time, right, it's for e in type 1 result plus equal the tuple of e. So this one is you are concatenating tuple, so it's it's also takes n steps. I think so.
Alright, you're correct. That this step for tuple concatenation takes n time. So I'll just put this as O n time. Worst case n time, because at the end of this loop, the size of this result is roughly n. It is n. So that's why the time taken to create a new tuple is going to be at worst n. But over here, you have the loop that runs n times, right? Okay, continue. Anybody else wants to explain?
Sorry if I hope I'm not interjecting. So for the second loop, I suppose it grows to m plus m, is it? From m plus one. That's
Right.
why
Okay. First, all right. How long will this step take?
as in the time complexity, is it?
Yeah.
n plus n squared.
This step, n
plus n squared.
plus m square. So where did you get that from?
Because for the second for loop, it starts off with m plus one, so it has the results from the first loop already. Then you
Yep.
will add like m amount. Yeah. So from n plus one you add to n plus m. Yeah.
Yep. At this point over here, result tuple is already length of n. So over here, the maximum size of the results tuple is already n plus m. Then over here, this loop runs n times. So over here, this loop is m times n plus m, which equals to mn plus m squared. So when you add everything together, you notice that you cannot just like take off any of these expressions. You cannot just say that you just ignore mn because you have m squared and n squared. Mn is a function of both m and n. So you cannot take off any of these for the final time complexity. So the final time complexity, you can write it as O n squared plus mn plus m, or you can simplify it to O n plus m squared as somebody else did. Now the reason because of why you can do this is the identity m plus m equals to n squared plus 2n m plus m squared, but you know that you can take off constants. Yep, you can take off constants. So that's why you can express it like this also. So is it actually ln tab 1 plus tab 2 to the power of 2? Yes, you can say that also. So either this or that can be accepted. Because n and m we are defining as the length of tab 1 and tab 2 respectively. So there's another question. I don't understand why is m plus n. Okay, look over here. After we perform this entire for loop at this point in time, where this comment is, the results tuple is already of length n. You can look through this in Python tutor also. It will guide you through the two loops that happen one after the other. So once we reach this step, right, notice that over here we are adding to the result tuple. This results tuple is starting from a length of n, and the maximum length that it would have been at the end of this loop is going to be n plus m, right? So that's why the time complexity of this specific step is bounded at n plus m. Yeah, so this loop repeats m times. So this particular block will take mn plus m squared time. So when you add it all together, it's n squared plus n m plus m squared, or you can simplify it to that. All right, other than that, I don't have any more questions already. So you all are dismissed.
Excuse me, sorry, I had one doubt. So the difference extra 4 is just the concatenation, right?
Oh, sorry, I can't hear you. Can you speak a bit louder?
The only difference between the extra 5 and extra 4 is the concatenation, right?
Hold on. Yeah.
So that's the one that's causing the That's the one that's causing the difference between the time complexities.
Yeah, it's because within the loop over here, we only have a O1 step. So incrementing the step counter by 1 is an O1 operation. Takes constant time. Yeah, so the loop, the number of time the loop iterates is relative to the size of tab 1, so n, and tab 2, which is m, and the step inside is O1. Whereas over here, the step inside it is complicated because of how tuples work. They are immutable. When you add a tuple to another tuple, it takes O(n) time relative to the size of the tuple. So over here, notice that the size of the tuple is going to be bigger, so it's O(n) plus m here.
Okay, understood.
Wait, sorry. Can you explain why the concatenation takes O(n) again? Yeah.
All right, let's see. Okay. So let's say we had a tuple over here. We save it to, let's say, 1, 2, 3. So how we represent this in box and pointer diagram is tuple 1, 1, 2, 3. So when we perform another step over here that says like tup plus equals to for a tuple with one element, what this is essentially doing, this is equivalent to make a new tuple with the elements of 1, 2, 3 and 4 together. So I'm going to make a new tuple 1, 2, 3, 4. And that obviously takes 1, 2, 3, 4 time, right? So that scales according to the size of the new tuple. So that is why tuple concatenation takes O(n) time, where n is the total size of the tuple. So notice that, let's say if I had, wait, first I'll show you the new diagram. So this will create a new tuple, 1, 2, 3, 4, and it'll reassign this to that. So you cannot add 4 to this tuple over here. You cannot, because tuples are immutable. You cannot edit a tuple afterwards. But what you can do is you can reassign the variable. The variable tup used to point to this tuple over here, right? But you are now pointing it to a different tuple. So let's see. Concatenation takes the whole length of tuple 1, which is n, while the previous problem, extra 4, only equivalent about 1. So O1 can be ignored, correct? Yes, because like O(n) plus O1 equals to O(n), because like you can take out the constant. Now, let's look at this scenario. Let's see. All right, I'll just clear this over here. So let's say we had a tuple of tab 1 is equals to 1, 2, 3, tab 2 equals to 4, 5, 6. What is the time complexity of this step? Tab 3 equals to tab 1 plus tab 2. Okay, Ashmi, can you answer this question? In general, like, let's say you don't even know what these are. So you know these are tuples. So what is the time complexity of this step? Okay, I'll just say it. The time complexity is O n plus m, where n is the size of tab 1 and m is the size of tab 2. So it scales according to the tuple, is the size of the tuples being incremented. So tuple concatenation is making a new tuple using the elements of these old tuples. And the time taken is O(n) plus m because you're creating a new tuple. It's the same way for strings. You know that strings are also immutable. So if you concatenate strings, it also takes the time of the total string, which is n plus m, or n plus 1 equivalent to n if you're only adding a constant number of like elements at a time. Now, if there are no further questions, I'll end the tutorial here. Will space be On plus M since it's reassigning the result tuple? The old tuple is discarded, or is it also no? Space, yes, space is N plus M. Yeah, because it's reassigning the old tuple. The space is freed up over here. Let's look at the space is freed up whenever you reassign a tuple, as long as nothing else is pointing to it. Like over here, if you reassign tuple to this new tuple, which you do when you do tuple concatenation, if nothing else is pointing to this tuple, Python will just free it up. It's not going to waste the space keeping track of stuff that nothing is pointing into it. So step one, this step takes On time because you're adding a constant of just one element. If this element you're adding to it is another tuple of variable length, then obviously the total time will be N plus M. Otherwise, if you're adding just 1 or 2 or 3 or any constant number of times of things, then it is O1 for the number of elements and On for the old length and total On. So we need to understand how this works. All right, you're dismissed if there are no further questions. Okay, I'm going to stop the recording. Thank you guys. Enjoy your holiday. Oh, I will enjoy my holiday. You guys haven't even started school. Why is the tuple concatenation of tup1 not On squared? Okay, why would you think it's On squared? 1 plus 2 plus 3 plus n. No, because those are constant integers, right? Because like you're working with integers, each addition of integer takes O1 time. Because like no matter how big the integer is, like if I were to set like n equals to 1, 2, 1, 2, 3, you wouldn't tell me that it takes 1, 2, 3 steps, right? It's one step, this is one step. This is one step. It's like 1 plus 1 plus 1 plus 1 for n items in tup1. So if you look at how a Python keeps track of integers, like the integer 1 takes up the same amount of space as the integer 10. So like the integer like 10 to the power of 6 also takes up the same amount of space as the integer 0. So you should like go look through like how Python keeps track of integers. Result at the start is empty. And it adds E. Oh, see, it adds E is O1 because it's always one element at a time. And now 1 plus E. No, you don't have to look at it like that. So just look at it over here. So over here, this step takes at most On time. So notice at this point in the code, the length of result will never be more than N. So we're looking at worst case. The longest time this particular step will ever take throughout this loop is going to be On, because that will be the maximum size of that tuple. So like in the first iteration of this tuple, yes, result is only one element. The second iteration, result is only two elements, but that will take like O2 time, right? And O3 time, which are all constant. But you notice that it is bounded by N. So this step will take at most On, which is why we use the big O notation of ON. O, big O means worst case. So worst case is ON for this step. So this step will repeat n times. That's the size of the tuple n. And this step takes n. So n times n equals n squared. All right. If nothing else, I have to go already. Bye bye.